Good afternoon, everybody. Thank you for joining us on our next of our QBEST audit webinars. Today we're doing one on big pumps featuring Phil Szabo from Saturn Engineering Group, who's been a long time auditor for the Energy Savers programs. And I'll introduce Phil in a minute. We've also got Jonathan online, one of my colleagues at Queensland Farmers Federation. Welcome, Jonathan. Just lost my cursor here. So I'll just give a quick. What we're going to do today is I'm just going to do a very quick intro to leave plenty of time for Phil to talk about big pumps and energy audits. We've got some time for questions, and then just a couple of wrap-up slides at the end with some next steps for people. I'd just like to talk about the Queensland Business Energy Savers Transformation Program, or QBEST program. As part of this program, funded by the Queensland Government, we're delivering 35 on-farm energy audits across Queensland on a range of farms. We've got loads of dairy farms, horticulture, cotton, sugar, and intensive animal farms, doing Type 2 and Type 3 energy audits on them, using independent contractors like Phil and Ryan Dillon, who you saw in the previous webinar. We go out and do very detailed audits on site and give the farms a detailed audit report based on the Australian standard for energy audits. And what we're doing also is to share the benefits of those audits with other farms by posting case studies about those energy audits on the Queensland Ag Energy Hub website, and I'll provide a link to that towards the end of the webinar. We've also been lucky enough to have a energy efficiency funding program available called the QBEST Energy Efficiency Rebates. They're currently closed, but if people want to sign up to our energy web e-news, we'd be happy to keep people up to date about when those programs become available again, both at the state level and federally. So at this point, I'd like to introduce Phil. Like I said, Phil's done a lot of energy audits with us, and we met Phil because he was doing the same for Ergon Energy in some previous programs. That little picture on the left-hand side or your right is Phil talking at a cotton energy workshop. I think that's in Bonshaw, Phil, that one, with a big centre pivot behind. So Phil's got loads of experience in his own business and through the University of Southern Queensland in detailed assessments of large pumps, both electric and diesel. Welcome, Phil, and thank you very much for your time and your expertise, and I'll hand over to you.
Thank you. Thank you, Andrew. Welcome, everybody. I'm just going to share my screen. All right, that's come up okay? Yep. So there we go. So the energy audits for the QBEST program from Saturn Engineering Group, we've conducted 9 audits altogether, 2 Type 2s, one on a feedlot, another on a piggery, and then 7 Type 3 audits, all focusing on pump stations for irrigation. So looking at a citrus farm, dairy farm, 2 sugarcane farms, and 3 cotton farms. I'll start with indicators that I use for measuring pump stations. So there's 2. One that I use for growers to monitor their pumps year on year is looking at the kilowatt hours consumed per megalitre of water pumped. So you can see here, we've got kilowatt hours per megalitre. The second one is what I use to measure or to look at each pump across all industries, whether it's on a cotton farm, on a sugarcane farm, dairy. They all represent, or they can all be represented from the second indicator, which is the kilowatt hours per megalitre per metre head. And for us at Saturn Engineering Group, I try to target around 3.8 kilowatt hours per megalitre per metre head for electric, that's electric motors. Diesel engines, when we're looking at how much diesel is consumed, it's 0.8 of a litre per megalitre per metre head. So you'll see that throughout this presentation and any work that I've done, these are two important figures. The first one, for the grower to use year on year to see how his pump is performing. Second one is more for me to see how the pump is performing overall. So we'll go to the first farm, which is a citrus farm. There were two identical Southern Cross pumps. They were connected in series, one after the other. There was one down in the river and then one at the top of the river bank. And their task is to irrigate 37,945 citrus trees. So there's 11 schedules, irrigation schedules. So that's each schedule is a different section of the farm to be irrigated. I looked at only 3 of those irrigation schedules, so I try to pick one at the lowest, with the lowest static lift, then one in the middle, and then one with the highest sort of static lift, which would generate the highest, and the furthest from the pump station, so generate the highest total dynamic head. What I found was that the pump efficiency ranged from 44.2% to 54.3%, and that's across both pumps. That's like each individual pump. So that's quite low. That's very, very low. Not a good pump efficiency. The energy usage ranged from 5.31 to 6.52 kilowatt hours per megalitre per metre head. The other thing that I found with this audit was that they were on the incorrect tariff. So they were on tariff 45, which meant that they don't pay a peak demand because their peak demand was below 100, just below 120 kilowatts, but they paid the higher network charges. So putting them onto tariff 44, they saved around $9,500 a year, almost 7.5%, 7.4%. So the recommendations from this audit was to employ a certified irrigation designer to check the irrigation setup, and then to install a VSD with only one single pump. So as you can imagine, that's quite a large job, which is outside the scope of a level 3 energy audit. And what engaging with the certified irrigation designer, we had a look at just using one of the pumps, one of the 150 by 125, 400 pumps, at what speed we could use it to see if we could get it to do one of the jobs in the 3 schedules that I looked at. And we found that operating it at 1700 RPM, it was good enough for, it could do the job for schedule 1. Saying that, I have, so the cost benefit analysis looked at just schedule 1, assuming that it was only irrigating that whole for that whole 12-month period. We found that the energy usage dropped to 3.67 kilowatt hours per megalitre per metre head. Pump efficiency was 79%. The electricity consumption reduced by 92,000 kilowatt hours. That's a quarter of the bill. And demand reduced by 27.9 kilowatts. So that was a saving of almost $20,000 a year. This, so this is a chart of the citrus farm's monthly consumption and their peak demand. So the orange line on top is their peak demand, which we can see is relatively stable. It doesn't, there's not a lot of fluctuation. So it's just below 110 kilowatts. Consumption varies. So we can see during the summer months, there is higher consumption, there is more irrigation, but during the winter months, our consumption reduces. I've also conducted a solar analysis. So when I do these, I look at at least three different systems, and depending on the interval data that I have, if it's not if the interval data varies over the over that 2-year period, then if the consumption varies over that 2-year period, then I'll look at varying the year or the segment that I look at. Since this citrus farm is relatively stable with their consumption, I've only looked at this one particular year, and I've recommended a 100 kilowatt solar system because the solar offset, the farm consumes 357,000 kilowatt hours a year, and installing solar would offset 177,000. That's based on the current interval data. Replacing the pump and looking at the irrigation system will reduce that further. So this solar analysis would have to be done again. But for what we've collected, a 100 kilowatt system is a suitable solution. That leaves 178,000 kilowatt hours that's imported from the grid, and almost 80,000 kilowatts that's exported to the grid. Now that 80,000 kilowatts, because they still remain as a SAC large customer, they're not going to get any feed-in tariff for that. So that's the citrus farm. Moving on to one of the cotton farms. Now this is an interesting one. There are 4 26-inch China pumps. And for those that know me, these 26-inch China pumps are my bread and butter. I've been looking at these for over 10 years. In this case, we have 3 electric and 1 diesel. I only looked at one of the electric pumps. I didn't investigate all 3. Of the 3 electric pumps, 2 of the pumps are on 1 NMI, and one of the other pumps is on a single NMI by itself. So that complicated the situation a little bit, as for the results at least, on how to do the setup, since we already have 2 NMIs there. So the results were that the pump is performing well. For a China pump, it could be better, but there's not much more that we can do to improve that efficiency short of continuing with the regular maintenance. Now, generally, again, those that know me can't believe I'm going to say this in a webinar, but the suction pipe on this pump was 660 mil. Now, for me, that's a big no-no. It's too small. The velocities are too high inside the suction pump. And I generally recommend to increase it to a 1050 suction pump for these 26-inch China pumps. However, in this case, if we increase it, we're going to reduce the total dynamic head further, which is going to take us away from the best, it's going to reduce the pump efficiency. So we're going to slide down the efficiency scale due to the lower total dynamic head. So, and the reason we can get away in this scenario with having the smaller suction pipe is because it has a flooded suction. So the pump is down the bottom of a well. There's 8 meters worth of suction pipe. And so therefore we're not going to experience cavitation with this particular pump because it has a flooded suction. China pumps are notorious for cavitation if they've got to lift too much. Just go to the next one up. So there was a lot of analysis trying to figure out what would be the best setup in this case, whether we have one, at first I thought we go all diesel. That would be the best outcome because electricity prices are getting so much higher. So I looked into various combinations, and it came out that the best combination was to have 2 diesel pumps, 2 diesel engine driven pumps, and 2 electric. If operations were less than 256 hours a year, then it was best to operate the diesel pump. If it was greater than 250, a month, I'm not sure if I said a year there, but if it's less than 256.8 hours a month, then we use the diesel pump. If it's more than 256 hours per month, then it's better to use the electric pump. So that's, and the main reason for that is to avoid the peak demand charges. So this has a peak demand of 160 to 100, depending on the level of the storage dam, 160 to 180 kilowatts. Paying the peak demand charge for that is quite high. So you can see I've turned it into a graph. We can see the cost of diesel. If we don't use it, doesn't cost us anything. Whereas for an electric pump connected to the grid, we've got that initial network charge that we need to pay for. And then on top of that, the moment we turn it on, we're paying the peak demand. So that line, and this is the first case that I've seen in my, 13 years of experience doing this. For the first time, the electric line crosses the cost of the diesel at 256.8 hours. So that was interesting. I found that, yeah, electricity costs are outstripping diesel. There are a lot of, like the numbers for this, the diesel costs I've included maintenance for the diesel engine, and from memory it was $2.81 per hour. The diesel costs were around $1.50 by the time you take out GST and excise. So yeah, it works out cheaper. All right, move on to the next. Sugarcane farm. So this sugarcane farm has, on the one NMI, there are 3 pumps. I've only looked at one, which irrigated one section of the farm. It's an 80 by 65, 280 Southern Cross pump. It irrigates 207 hectares of sugarcane with laterals, travelling guns, and flood irrigation, depending on the location on the farm. What I found was that the pump is operating well. It is a 25-year-old pump, and pump efficiency was 72.5%. Can't complain about that. Energy usage was 4 kilowatts per megalitre per metre head. Also a good number, could be better, but I was happy with that. However, I did find that the friction losses in the system were 68.9 metres, and also that there was 46% loss in water flow rate. So the water required is 35 litres a second. I measured 30.9 on the suction line going into the pump. When I measured the water again coming out at the lateral, it was 39 minus 40, 14.2. So the losses were 14.2 litres a second.
Phil, sorry to interrupt. Phil, can I just ask you to let us know what the size of the motor was as well, please?
The motor is a 45 kilowatt motor.
Thank you.
On this one. Where was I? So yeah, there was significant losses, water losses, plus high friction losses within the system. Again, it is best to engage a certified irrigation designer. There's 4.7 kilometres of main lines and sublines to replace. So it's not a small job by any means to replace all of that. And it is looking at increasing the pipe diameter from 150 mil to 200 mil pipe. Doing that, it reduced the friction loss. So where we assessed this pump, it was 1.3 kilometres, 1 kilometre along the main line and 300 metres along the subline before we had the pipe coming out from a hydrant into the lateral. So for this assessment, the total dynamic head was 98.5 metres. Replacing the pipe reduced it down to going from the 150 mil to 200 mil pipe, reduced the total dynamic head down to 49.5 metres. The electricity usage, so the number that we're interested in, that the grower's interested in, that we spoke about at the beginning, went from 393.6 kilowatt hours per megalitre down to 197.9. So that was a significant savings there. Looking at this, replacing the pipe, we're also saving the water. So there's the additional costs in the water savings. There's also additional costs now. I've also looked at running 2 laterals at the same time. So changing the pump over so we can get 60 litres a second if we want to run 2 laterals. So there's additional savings in labour by doing that. And then we can also, there's another small section of the farm where we've got a 55 kilowatt pump that's irrigating through some laterals. So there's potential to get rid of that completely and use this pump as well to irrigate another side of the farm. So this particular sugarcane farm already has a 30 kilowatt solar system installed. We can see from the interval data that it's very weather dependent. If it's a dry period, there's high consumption, as we can see in March, and that pump pretty much didn't turn off for the month of March. However, in the following, the pumps, don't forget there's 3 pumps on this one NMI, so this isn't just the 45 kilowatt. We've got another 45 kilowatt and a 55 kilowatt pump as well on the one NMI. So we can see that consumption for March is quite high, but then the following months there's not a lot of use. So it's a relatively wet period. This particular farm does switch from the SAC large to the SAC small, or has the potential. So some years they are over 100 megawatt hours, and other years they're under, even with the 30 kilowatt system. So by upgrading the pump, it gives the farmer greater flexibility to be able to irrigate just through the solar producing periods, which understandably does affect the application efficiency as well. But it's where's the money going to be spent, on the water or on the electricity? In this case, it does seem that due to the cost of the water, it is a little bit cheaper than and to be able to pump that water than it is to pay the electricity bill. Or it's beneficial to try and keep it under that 100 megawatt hours to stay on the SAC small, and then we get the feed-in tariff as well. So you can see in the chart, the feed-in tariff is important in this case because the green bars are what's been exported to the grid, and we're not getting any feed-in tariff for it if we're a SAC large consumer. Yes. So this is the month of March. We can see how much of this is the energy flow through the month of March, where we only had the 45 kilowatt pump running for this particular month. We can see that from midnight, we're consuming 45 straight across. As the sun comes up, then our consumption starts to decrease. 11 a.m., our consumption's at a minimum, and then it starts to increase again as we go through to the afternoon, and 6 p.m. we're back up to 45 kilowatts and straight across towards midnight. This little area here, there is the decrease here. When I looked at the data, it just seems to be a period where the pump is switched off at times. So it's a little anomaly in the data, and I just chose not to take it out to highlight. This is where the pump gets switched on and off. So for that, there was a 15-minute period in there that's come out in the data. All right, moving on to what do we got? Another cotton farm. So this one, we've got a bore pump, 75 kilowatt bore pump. It's a 4-stage Flowmax 8SH submersible pump, so there's no line shaft involved for this one. It was upgraded 18 years ago, hasn't come out of the hole for 18 years. There's been no maintenance conducted on this pump in that time. The pump's task is to lift irrigation water into a storage dam, which was the furthest point, and there are 2 irrigation channels. There was one right at the bore pump site and another one a couple of 100 meters down the road, and the storage dam was about half a kilometer down the road. So it is the right pump for the task. However, there was water missing. Now we're not sure if the water flow rate was about 25% below what it should have been according to the pump curve. Now we couldn't figure out whether it's due to wear and tear on the pump or if there's a hole in the bore casing and it was just recycling the water through. So because the water measurement was taken once the water came out of the ground. So the pump efficiency was ranged from the 3 duty points between 56 and 58, or almost 59%, which was low for the pump. Energy usage was between 5.04 and 5.29 kilowatt hours per megalitre per metre head. The water flow rates were low. The pump hasn't been removed in 18 years. And yeah, as I was saying, we didn't know if the performance was due to the pump itself, or a hole in the pipe, or a combination of both. At this stage, the pump still hasn't been pulled out of the ground. So my feeling is it's a combination of both wear and tear on the pump and a hole in the bore casing. The recommendation was to obviously pull the pump out, conduct some pump maintenance, and reline the bore if required. That would improve the pump efficiency to 77.2%. And it was relatively close, like for the 3 duty points, they're all very similar, within a percentage point of each other. We get additional 25% of the water, so we're not recirculating that water. Energy consumption was reduced by 28,000 kilowatt hours, or 23%. Again, so this was, actually we'll look at that in the solar analysis. So this is, yeah, so we'll look at the solar installation, which will tell more about the energy consumption. First, we'll look at the consumption over the 2 years worth of data. So we can see from the first summer period captured, the pump was only used in January, February. That's great. Can't argue with that. No problems there. But when we look at the following year, the pump was used for a day and a half in November, and then only half a day in March, and then all through December, January, February. This day and a half use in November cost an extra $2,000, just under $2,000 in peak demand charges, and the same for March. That was about 8% of the total bill for that particular year. So the total cost was $45,000. And yeah, there's an additional $4,000 in charges just because we used the pump for a day and a half on one side and half a day on the other, almost a day on the other. So it's important to know, if we're on SAC large and we're paying for the peak demand charge, do we really need to use that pump for that day and a half, or can we wait until December? One of the key findings. Now, solar. Recommending solar for a situation like this, there's not enough usage to warrant like a solar to reduce consumption. The only way that I'd recommend solar in this case is to try and keep it below the 100 megawatt hours. And even then, we can see in the 23, so I've broken it up into 3 years. There's the 2022 year, the 2023 calendar year, and then we've got the 22-23 financial year, so going from July to June. So from that, I've been able to create 3 lots of data to analyze for solar, whether solar's recommended or not. We can see down the bottom, the blue lines, this is, or the blue bars, I should say, this is our solar offset. So in 2022, there's not a lot of solar offset. There's no point in installing solar. Also, our consumption is only around 50,000 kilowatt hours for the year. However, when we look at the 2023 year, our consumption has gone up to over 200,000 kilowatt hours. But again, our offset for a 30 kilowatt system is only low. It's just over, it's 11% of our total consumption. So our self-consumption is 11%. So again, it's not really worth installing solar to try and offset our consumption, or in that case, to try and remain in as a SAC small customer. Again, looking at the financial year 2022 and 2023, our solar offset for a 30 kilowatt system is only 13 kilowatts. So 12%, 11%. Again, our self-consumption is too low to warrant installing a solar system. So the lessons that we've learned, pump maintenance is a big one. So we've seen here that a pump that hasn't been pulled out of the ground for 18 years, there's improvement there. That the payback period for replacing that pump was just under 5 years. And it's something that I do recommend, rather than pulling out the pump every 5 years to find out if there's something wrong, monitor the kilowatt hours per megalitre. So keep a track of that, your electricity bill and your water bill, divide the two into each other and see what that is. If that starts to creep up, then it's cheaper to get someone out like myself to look at that pump rather than to pull the pump out. I might say yep, we can run this pump for another 2 or 3 years before it warrants pulling it out. Or if we do it now, then it's going to be paid back in 3 to 5 years, whatever it might be. Looking at the pipe network is another, or pipe network maintenance is another key learning from these audits. So there's pipes there's a lot of fouling that occurs inside a pipe, and it can be very thin to start off with. It does have a dramatic effect on our friction losses and can increase it rather quickly, reducing pump performance. So it is important to make sure that the lines are clean, that the water going through is clean, that the pipes are maintained, particularly with the water losses. 46% is quite a lot. One of the largest that I've seen. So it's imperative to make sure that our pipe network is kept up to date, or maintained, well maintained. Pump selection is another key one. So with a couple of cases that we've seen here, where for the citrus farm and the sugarcane farm, a pump selection process is imperative. Once we've sorted out what the pipe network is, we need to design the system and then select the correct pump for the task. If it's not the right pump, then we're not operating at the correct efficiency point, and we end up paying much more. Something that I haven't seen in this, I have on another site which hasn't been finished reporting on yet, but the suction design and suction pipe is imperative. We want to keep our water velocities quite low in the sump, and the limit that I use is 0.3 of a meter per second. If you can imagine that the water, the weight of water, 1 cubic meter of water weighs 1 ton. And when we're moving that in one particular direction and we want to change that direction, that's a lot of weight. That's a lot of energy that goes into it. So we want to keep those velocities quite low. We want large suction pipes to keep those velocities low. I do see it predominantly, like I have recently looked at 26-inch China pump. China pumps, not a 26-inch, but a China pump that had suction design problems. It was too high on the side of the storage dam. The water level the tail water return was there's 4.5 meters. So there were issues with that design. The only way to fix that pump was it could be changed out to a different pump that ran at a lower speed. So a 20-inch would have been better for the job, or lowering the pump 4.5 meters. Can't stress the sump design and suction pipe design enough. If it's not right, we move on to the next point, cavitation. So I just want to highlight cavitation, the difference between cavitation and air entrainment. There is a difference between the two. Cavitation is the water boiling. So if you look at your pot sitting on a stove heating up and you get those tiny little bubbles on the bottom of the pot, that there is the water changing state from a liquid to a vapor. That's what occurs on a pump. It changes state. The pressure gets low enough that it changes state from a liquid to a vapor. And as it goes from a low pressure system in the pump, from the suction side of the pump to a high pressure system on the discharge side, that little water vapor, that vapor molecule, sorry, implodes on itself, and that energy needs to go somewhere, which goes into the pump, into the impeller. Air entrainment is completely different. It does affect the pump, but all we've got is air, atmospheric air that goes into the pump. As it goes from the low pressure system, the air bubble will expand to become larger, but as it goes through the high pressure system, it'll just contract, become smaller, but it doesn't implode, or it doesn't cause damage on the pump impeller. It does cause imbalances. If there's a lot of air entrainment, it will cause imbalances within the pump. So it can have vibrational issues. Again, if you look at a cubic meter of water weighs 1 ton compared to a cubic meter of air weighs 1.8 kilos, just that little bit of air going through the pump can cause those imbalances. And the last one is the pump operation and scheduling. So ensure that the scheduling is done in a way that matches the pump performance, and particularly pump operation. So Andrew alluded to an example that I've used in the past where a grower asked me whether to use 2 pumps running at 1200 RPM, or do I just use 1 pump, but what speed do I run that 1 pump at? So, and through the work that I did for him, we found out that if he just operates 1 pump at 1400 RPM, he gets the same amount of water, but at a cheaper cost than running 2 pumps. And that, is me finished. Thank you very much, Andrew.
That was great, Phil. Thank you.
Sharing my screen.
And that was great. Thank you very much, and very detailed as usual. And I'd like to, just like your audits, and I'd like to just give everyone a chance to put some questions in there. But those, just while they do that last point, the last series of points that you raised there, go to the irrigation system designer that you mentioned in a couple of your recommendations in the audits. Don't they, where you sort of get someone that can look holistically at the crops, the crop water needs, and the whole system.
Yep.
Whereas you're obviously, the way you do your audits is very holistic in that you're looking at the pipe system and the total dynamic head throughout the system, but having the system designed by that irrigation system designer is very beneficial.
Yeah, so what we're looking at is if we've got a lateral, we need a certain pressure at the lateral, and then we want a certain flow rate. The flow rate's not going to change through the pump unless we've got losses in the system. But we start with the pressure that we require at the lateral. We take that, and then we add the friction losses in. So that's just the water flowing through the pipe, creates an additional head. And then on top of that, we've got the static elevation. So wherever the water is sitting, wherever it's coming from, a storage dam or a river, to where it's reaching atmosphere. So if it's going into another storage dam or coming out the lateral, that elevation. So they're the 3 key ones. There are a couple of others, but we'll keep it simple. They're the 3 key ones that we want to look at when designing these things. So when we saw that we had 68.9 meters of friction losses, there's something that we can do about that. Increasing pipe diameters, keeping it clean, are some of the things that we can do, particularly across 4.7 kilometers of pipe network. It's a big job. So, and it just, if our pressures increase too high, then we're going to lose our flow rate. So if the friction losses keep getting higher and higher, we're going to lose our flow rate. That will reduce. It's a trade-off. If our pressures are low, our flow rate will be higher. And depending on the pump as well.
Yeah, okay. And so that, just staying with that one, seeing you brought it back up, you might look at the recommendation and think that's going to cost me a lot of money to upgrade that much mainline from 150 to 200 millimeters. And purely on the electricity bill savings, it might take a fair while to get a payback on that. But you mentioned the other benefits that the farm would see around flexibility, being able to use other irrigators, using two irrigators at once.
Yep.
There's not just bill savings, Phil, are there?
No.
There's other benefits.
Yeah. So the electricity savings, when I first did the analysis, it was like 88 years, the payback period for replacing the pipe. It was a $250,000 job to replace the pipe. And that doesn't include the pump selection, like changing the pump over or installing the VSD. That was just the pipe itself. But on top of that, there were labor cost savings, there was savings in the water. And then I looked at increasing production as well. So this particular farmer did a little bit of research himself by adding more water to his crop, trying to get it on at the right time. And the profit gain by getting his irrigation right. I'm trying to remember what it was. There's a significant increase in his bottom line. So applying that methodology to an additional, what was it, 287 megalitres that he's now saving. Yeah, that's increased his crop yield, or potentially increases his crop yield, which I've taken into account in the analysis.
Yeah, that's good. So it's worth not just sticking to the electricity cost savings when we do these audits. And then the other one I just wanted to ask about the solar on the cotton farm with the 75 kilowatt. Because yeah, I mean that in that 1 year that you showed where they were below 100 megawatt hours per year, they would get a feed-in tariff if they were able to. I mean, they'd have to apply to and be approved to be reduced to a SAC small customer to be eligible for that. But like you said, it's like with such concentrated use in just a couple of months, it's very difficult to sort of clip
Yep.
the high consumption off with a small solar system. So you'd
Yeah.
have to go with a really big solar system to cut it down to a small user year on year, but then the cost of that in the space would not be viable to do that.
Yeah. So where they've got in 2023, they pumped a lot of water. So it's over 200 megawatts that they've consumed. Trying to get that under 100 megawatts is near on impossible, even with solar. I mean, solar batteries, you're looking at, what would it be, 300, $500,000 plus
Yeah.
for a system like that. And it's just not viable. I don't see that it's viable. I wouldn't want to spend that sort of money. So of two of the even looking at the 2022-23 year with a 30 kilowatt solar system, it still didn't bring them under. So they've got 120,000 kilowatt hours. It still didn't bring them under.
No. And so what those pump efficiency upgrades would do, like bringing the pump up and having a look and making those repairs and reducing the consumption by as much as you estimated would probably increase the number of years that they would remain a SAC small customer on balance. So they'd still have their very large consumption years and they'd have their smaller years, but it would, they'd have to run the pump a lot more to become a large user with that volume of saving.
And that comes down to their allocation.
Yep.
So we need to use their allocation when doing these assessments. If they've got 100 small allocation, 100 megalitres or 200 megalitres, then yeah, we need to do those calculations based on how much water they've got. And then there's also the issue of carryover. Some have carryover each year as well. So yeah, it's not an easy one to solve. And I mean, some farmers like to go green and install it. But you need the usage. You really need that usage throughout the year, not just 2 or 3 months.
Yep. Excellent. And speaking of ones that may not be easy, someone's asked, how easy is it to check for fouling and understand what any metrics there are on losses for fouling of pipes?
So one of my colleagues in the industry, he focuses a lot on this area, and the networks that he looks at, they're quite long pipe networks, and he does a process called pigging, where he inflates like a balloon and puts that through the pipe to clean it out. Now all it is just cleaning out call it the mold or the mildew or whatever it is, the like a little bit of green fouling on the inside of the pipe, and you can see the dirty water coming out the end. So it's, yeah, you stick your hand in there and you can feel the slime coming off. That apparently is enough to cause these sort of losses, significant losses. Even the small, like the debris that you see on the bottom, the sand, the silt, increases the friction losses. I was blown away when I saw how significant they can be. So you'll see the large users, particularly it's sort of transferring water over kilometres. They have to clean their pipes on a regular basis, otherwise the pumps can't keep up.
Yeah. Okay, thanks. And I've got one more question just around how you measure the water efficiency impact while you're doing the audits as well.
Water efficiency, how I measure it?
Yeah. The impact on water efficiency of the energy efficiency upgrades that you recommend.
I don't measure the water application. It is best to irrigate overnight rather than the day due to evaporation losses. I do recommend putting in soil moisture probes to pick the times for irrigating, but I don't specifically measure water. It's sort of looking at, if I know the crop, then it'll be looking at the research being done in that area. So on individual farms, unless they want an application efficiency test, it's not something that I do for an energy audit.
Okay, fantastic. Well, I think that's all our questions. So yeah, I'd just like to say thanks again, Phil. It's been great to have you on, and very detailed and comprehensive, as usual. Like I said, just like your reports are. So I really appreciate you giving up your time for this webinar. We're going to put this webinar on our Ag Energy Hub as a recording, and we'll just do a quick summary article, and we'll set the chapters up in the video so that people can go straight to the various case studies that you've talked about when they go and watch the presentation. I'll just quickly on the Ag Energy Hub. It's a new online resource that we've established as part of this QBEST project. That's the website at the bottom there, queenslandagenergyhub.com.au. We've put a lot of resources on there from our earlier energy case studies through Energy Savers, and we're gradually adding new case studies like the ones Phil's presented today. We'll be adding all of those from this QBEST program onto that over time. It's a really great resource. You can look for, you can search for through case studies by sector, location, technology, irrigation style, and those kind of things. So it makes it easy to find what you're looking for. And there's other general energy sector information as well, like our Queensland Renewable Energy Landholders toolkits on there, and other similar matters relating to sort of the energy transition. Jonathan and I and our colleague Sam are also working on the EnergySQ program, which is doing type 1 energy assessment. So we're talking with Phil about the type 2 and 3 assessments he's been doing. We're doing type 1s, which are more simple assessments of energy efficiency, energy consumption, with a walkthrough assessment and a bit of carbon advice. And we're inviting farms in those 6 local areas on screen there: Southern Downs, Gundawindi, Western Downs, Toowoomba, Lockyer Valley, Scenic Rim, to contact us at QFF, and we'll include you in that and do that energy assessment with you. We do have 3 more webinars coming up. There's There's one on scheduling energy consumption to maximise your solar by Stephen Sutar, and some of you might remember him from one of the microgrid webinars we did. Another one on aquaculture, voltage, power factor and variable speed drives, looking at a case study of a North Queensland barramundi farm by Alan Day of Tailored Energy Solutions. And we're also still hoping to bring you one on energy efficiency opportunities in piggeries, probably sometime in November as well. And last but not least, our energy information service for landholders. So you can see that telephone number at the bottom right there. So any landholder in Queensland can give our energy team a call and ask us for advice or information about anything from tariffs, energy efficiency, renewable energy, or the energy transition, such as projects that might be under construction or under development near the landholder's farm, and we can sort of help put you in the right direction for good advice and information. And that's about all we have. So there's the contact details there, and we'd welcome you getting in touch. And once again, I'd like to thank Jonathan, my teammate here at Queensland Farmers Federation, and a big thanks to Phil Szabo for presenting to us once again. Phil, thanks very much.
Thank you.
All right. Thanks, everyone, and go off and enjoy the rest of your Halloween. Thanks again from QFF, and we'll see you for the next one in a couple of weeks. Thank you.